Can someone just chat real quick or let me know they can hear me and that everything's clear? Someone able to let me know that they can hear me and that everything's working okay? Okay, thanks, Will. Okay, great. So let's go ahead and begin. This is the second part of the introduction to architectural computational solvers. The first part of that presentation was a real basic overview of the concepts, and this next one will be dealing with kind of the nuts and bolts of how a computational solver is used within an architectural context. And mostly I'll just be kind of going over the interface and how to use them. So as a quick overview, of course, you can think of all of the different solutions that a solver derives as tensors. And you can plot those tensors in a field, basically like an X, Y, and even Z coordinate plane. No audio. No audio. How about now? Is the audio working? Is the audio working? No? Hmm. Looks like we're having audio issues. Speaking. Hello? Is that better? Can anyone hear me now? Ah, Tim says he hears me. Tim says he hears me. Maybe Will is having troubles. Okay, great. So let's go ahead and begin. So this is the second part of the introduction to architectural computational solvers. The first part of this tutorial was a very high-level overview of the idea of a solver and what it is and how it's used and what it's good for. This next section will be a real nuts and bolts type of a tutorial dealing with kind of the interface and basically how I would go about using a computational solver within an architectural context. So let's dive in with just a quick review. The basis for solvers is this idea of creating solutions for a problem, and usually this problem involves some sort of a logic or mathematic base. And within that, you end up with solution sets, and these solutions can be termed tensors, and those tensors can be plotted, and they can be plotted in a three-dimensional way with a high point and a low point, and usually a solver solves for the high point or the low point. Of course, the complexity can become overwhelming for computers, even today with our massive amounts of computational power. So it's important to curate your data sets that you're starting with. And then there's ways you can do that, but it's important to be careful that you don't over constrain your data sets. And I talked about that extensively in the first solver. Here's a quick list of some of the computational solvers that you can find within the Grasshopper ecosystem. There's additional ones that are within Dynamo, and of course there are computational solvers outside of the architectural software kind of realm or market. So I first wanted to talk about the case study that I use, and this is a building that's in Washington, D.C., and there was this big push to incorporate curved glass in the facade, both from the client and the design side from us, and then also from the municipality of Washington, D.C. They all wanted this curved glass, which is great. The problem was coming up with a radius that worked well. And so there was a lot of iterations that were pushed through the design process. And eventually they determined that there were some constraints that were important. It was important to have 48 inches in depth and 480 inches in length for the glass. And then there was also this constraint of having a 60-inch radius on both curves, both of the acute curves. But what that meant was that with these tight constraints, there is actually no real solution, no rational solution. This diagram shows a solution that is accurate to 2 significant figures beyond the decimal point. But if you go to the third decimal point, the third figure beyond the decimal point, it actually doesn't solve, which makes it difficult for a human to solve this problem. There's no, like I said, no rational solution, which makes a solver a perfect tool to try and solve this problem. So let's go ahead and dive into the actual Grasshopper interface. So here it is inside of Rhino, and there's actually nothing in the Rhino interface. It's all within Grasshopper. So if I were to hide this, there's nothing there. It's all in Grasshopper. And if I were just staying at the zoomed out level within Grasshopper, you can kind of see 2 main components of the script. You can see the actual script. Yes.
Can you hear me? I think the screen is frozen.
Oh.
Is there any way you can update it? Seems like we're stuck on the title slide.
Oh, really?
Mm-hmm.
Thanks for popping in here.
No problem. It sounds really good so far, though.
You know, it's funny. I tried recording this twice earlier in the day, and both times had glitches. You know, because I'm in China, and so it's midnight here. It's 12:50. So, man, this one just doesn't want to be recorded for whatever reason.
Right.
But anyway,
Okay.
hopefully it's
I see it now.
updated.
It looks
Yeah.
good.
Okay.
Yep. Thanks.
Yeah, thank you. So here we are within the interface, and like I was just showing, this is the script itself, and then all of this is kind of solvers that I've put into the Grasshopper environment in order to try to solve for the problem. So again, if I turn off everything in Grasshopper, there's actually nothing in Rhino, as you can see. And Tim was gracious enough to create a Tuesday training about clusters. And what I've done basically is I have put everything regarding the design of this script within a cluster. And then I have out here, I have the dimensions. So you can see those in green. If I select it, you can just see that all it is the dimensions. And that's strictly for me to try and, or for us to try and understand how accurate the solver is being, and to get quick feedback on, you know, the accuracy of the solution. So there's kind of some basic components to this. The first one is you have to set up a Grasshopper script that is organized in a way that makes it easy for a solver to solve for the solution. And essentially what that means is that you want to have an output that is either a high value or a low value. So here we're looking at this output. You can see when I select it, it's coming out of my cluster that's organizing this script. And what's happening is I've determined that the best way for us to evaluate this particular solution is by trying to minimize two particular triangles. Basically, we want those triangles, the length of those triangles, the length of the curves that make up those triangles to equal 0. And if we can get that, then we've arrived at our solution. And those two triangles are located at these 2 points. So if I go ahead and flex the muscles of this solver, or sorry, of this script, you can see here, let's see here. Oh yeah, here we go. So basically the parameters that we're using to try and solve this solution are the radius of 2 circles. This larger circle, which is going to take a second to update here. This larger circle here, you can see it changing size. And then this one of these smaller circles, and the two smaller circles are constrained together, so that if one changes, the other changes in size. There you go, you can see that adjustment. So that gives you an idea of how I've set up the script, and that I think is actually the biggest part of using a solver within your workflow, is actually setting up the script in a way that a solver can read it. And so let's go into that a little bit more. Essentially, like I said, there are kind of two parts that the solver is interested in. The first is your input sliders, and that's what are referred to as the genome. And Grasshopper has this kind of nifty tool called the gene pool, and it's just a bunch of sliders in a single component, which allow you to get a lot of variable data quickly. I tend to stay away from that just because if you're going to use a gene pool, you're most likely going to have to separate them out by using indexing, and so it's just easier to use individual sliders. And the nice thing about using computational solvers is that you can connect as many different sliders as you want to the solver. So that's the most important part, is that these input sliders that determine how your definition will change in relation to the inputs, and then obviously, like I talked about, these outputs. Now, I guess let's dive in and talk about Galapagos. So Galapagos is the computational solver that comes with Grasshopper. It's built in. It was designed by David Rutan, and you can just click on it on the toolbar and drag it onto the canvas. And there are two main parts to it. There's the input node on the far left, and then there's the output node on the bottom. And the way it works is that you drag out a line from this input node, and it will snap to any slider. And if you want to connect multiple sliders, you hold down the shift key, and that allows you to connect multiple sliders. The thing about the Galapagos solver is that it can only connect to one output solution set. And so here we're connecting it to this number component. And so essentially you type in number, and that gives you that component. And the way that I'm deriving this number component is it's just the average of these two numbers. So, or it's just the added value of the two numbers here. So essentially takes the size of triangle 1 and the size of triangle 2, adds them together, and it gives you an output of that. And so it takes these two inputs and tries to come up with the optimal solution that gives you the either maximum or minimum value for each of those. So the way that most solvers in Grasshopper work is that you can double click on the component, and that brings up an interface with values that you can set. And generally, my rule of thumb with the computational solver is you just want to use the default settings unless you have already exhausted those default settings and it's not giving you the solution you want. And then it's time to start to manipulate those settings. So in our case, we actually want a minimum, and that's actually the most important piece of information to adjust is what is your fitness requirement? Is it a maximum or a minimum? And all the other stuff is kind of fluff or not as important. But obviously, you can see that with an evolutionary solver, it's based on this idea of this metaphor of evolution, and there's a lot of mathematics that's kind of driving this idea of an evolutionary process. And with that, with this metaphor, you have kind of a population, and you have kind of generations, meaning that what happens is that it eliminates a number of the population till it comes up with optimal solutions in a generation. And then it will take those those best case scenarios and move them to the next generation to start the next generation, introducing kind of more inbreeding between the the population that's been selected. So then within the actual solver interface, there's kind of 3 graphs, and now it's probably a good time to switch over to the other one that I have running here. So this one I've been running for 15 or 20 minutes now, and it looks like it's still going here. So you can see on the left screen, it's actually kind of adjusting the script and looking for best case solutions. And so here you see on the top with this orange are the generations. And so we're at generation 35 now. On the bottom of the screen, you can see a graph with all of the different solutions, and the X's mark the solutions that don't make the cut for the next generation. And then you see this connecting graph showing the different variables and how it all interfaces. And then in this last one here, you see so there you can see in that graph, this is one of the solutions. But so here we see that it's solving for the optimal solution, and this is the best one that's found so far, with the combined triangular length of 0.03. So we're getting close to that 2 significant figure value that we're kind of hoping for. So there you can see, the sliders are moving around quickly, and you can see the output values adjusting, and you can see the actual script adjusting the geometry in the Rhino window. It's kind of a fun process to watch, and often when I'm doing something maybe more with solar paths or something like that, it's something that's worth recording or taking screen grabs of so that you can show later on your process and that you've tried to solve for the optimal solution using a solver. So let's jump back to this other one here. Let's see if we can get it. Okay, here we go. So that's Galapagos, and that's the one that comes with Grasshopper. And we'll do a completely different tutorial about Octopus, which is a multi-fitness solver. And the difference between Octopus and most solvers is that Octopus allows you to skip this process of combining your different solutions sets, and you can go straight to the original solutions. So what it will do is that Octopus will try and solve for a 0 in triangle 1 and a 0 in triangle 2, as opposed to kind of this combination of values. Now, there are a lot of computational solvers. So of course you have Galapagos, and then these are some additional ones that I've installed. You have Opossum, which is also, they're working on a multi-fitness solver as we speak, and that should come out soon. And then you have Goat here. It's got a similar interface, and that one, and then you have some others. Here's Octopus, like I said, but let's see here. You have this other one, Crow, which has a number of artificial neural nets and also some solvers in it, and Dodo. And Dodo is really great because it has both artificial neural nets and solvers, in it, and it has several of them. So here's two of the ones that come with Dodo. But as you can see by the plugin, he's really dedicated himself to trying to work out the tools required for solving for solutions within the Grasshopper environment, and they're using different mathematical algorithms for the basis upon which they're finding solutions. So if we double click into Dodo, it's similar to Galapagos, but not quite as nice of an interface. So if I'm just going to again keep those standard default settings, and I'll just hit start here. And similarly to Galapagos, it has a graph kind of showing the different potential solutions. Unlike Galapagos, with this Dodo solver, you're not able to actually scroll around within the interface. It's kind of locks your Rhino and Grasshopper interface up. Here we are with Dodo in, it looks like 25, 30 iterations now. And with no change. While that's running, maybe we'll go back to this one with Galapagos. Again, because this is an irrational solution, you end up with Grasshopper kind of waffling around and never actually reaching a real solution. If it reaches a solution, it will usually plateau and kind of go to the top. And that's actually one reason why the solver is continuing to go 48 generations, because essentially it's not finding a real strong solution set. When I actually ended up solving this problem, I didn't end up using Galapagos, and I don't even think I used Octopus. I think that I used possibly another solver like Dodo or something. I'm not, but so that's one of the things that's important to think about, is that the solvers do solve differently, and because they solve differently, sometimes you'll get better results with different solvers. So it's worth your time to try different solvers to try and come up with the solution you're looking for. Okay, so that's kind of the traditional solver ecosystem or but you end up having these other types of solver interfaces. The next one I'll talk about is artificial neural nets, and from my experience with artificial neural nets, within a traditional architectural workflow, an artificial neural net isn't actually that useful. And the reason I say that is because what ends up happening is that an artificial neural net, here are two examples. You can see probably one is from the TT toolbox, or one is from the from Nate Miller's work, and then I think the other one is from Crow. But the problem with an artificial neural net within an architectural context, and I actually believe in many contexts, is that it requires a solution set, meaning that you've solved the problem one time. And once you've solved the problem one time, often the parameters of the problem change, and it becomes difficult to reuse the solution set for the new problem. And so within a design context, the solver will help you to solve the problem, and that will give you the data set necessary to use the artificial neural net. But usually, once you've solved the problem within a design context, you're moving on to the next phase of the project, and you're not trying to solve that problem again another time. Now, we actually do have opportunity to use artificial neural nets in the context of Reach Urban Plan, Reach Campus, and potentially Reach Tower. And so we're kind of excited about that, and we're looking forward to trying to integrate a neural net within that workflow. But that's experimental and down the line, so we'll see how that develops. The last one that I want to cover isn't necessarily a solver, but it's called Design Explorer, and it's made by Thornton Tomasetti, and it uses this tool called Calibri to help you to interface with what they call Design Explorer. And essentially what it wants to do is it wants to connect to your input parameters and take note of those before they go into whatever you're solving for, whatever you're trying to get solutions for. And then on the back end, it then will produce data that will allow you to analyze your solutions. And it asks for a location on your hard drive to save out some information from Grasshopper and Rhino, and then it allows you to actually analyze the solutions you have. So let's pop over to Design Explorer. This is the interface created by Thornton Tomasetti. And I believe that Tim Williams and Will Wang actually met some of the people who were instrumental in creating this at the most recent TT meeting in New York City. Anyway, so here you have Design Explorer, and it's essentially taking the process of a solver and then kind of freezing it and then kind of flattening out that process and allowing a designer to kind of see inside the black box of the way a solver works. And so you have the kind of inputs on the left, and then you have the output or the solution sets you're looking for on the right. And so, we can say we want a solution where the triangle 1 and triangle 2 are minimized in terms of their size. And so then it gives us kind of a list of the best solution sets. And so these are some of the best solution sets and there's a glitch obviously, but these are some of the best solution sets that were found from the data set that we started with. But it's very robust in terms of kind of helping you to analyze different design options. And so you can imagine a designer could use this tool with his project manager to kind of go through design options that are interesting and may meet the requirements. And obviously there's a lot of tools and in this interface, like you can choose to kind of star one solution or multiple solutions to allow you to kind of start to evaluate these. And then obviously the interface is very malleable, allowing you to really play with how it all comes together and what all you're seeing. So this is a really great tool to try and integrate with something you're looking to try and solve for. And it kind of gives, like I said, it gives you the opportunity to kind of flatten out that solver process and understand all of the solution sets that the solver may be kind of working through. So with that, I think I'm finished with today's tutorial, and I'll take any questions that anybody has. there are no questions, then I can end and say goodbye. But thanks a lot for participating today, and I hope you found something useful for you. I guess I'll sign off. Feel free to contact me offline if you have any questions about what we talked about today. Thanks a lot. Bye.